was saying AK plus 1 divided by AK is approaching R. That's the hypothesis, right? I was actually saying more that if this absolute value is converging to R, it's even better condition. Then we conclude absolute convergence. Absolute convergence implies usual convergence, right? So that's good. So as k approaches infinity, if that makes sense. Then from here we can pull out a little comparison with a geometric series. Right, AK plus 1 divided by AK is not exactly R, but it's very close to R. And then what we know about this R is actually less than 1. R is not approaching 1. R is a fixed number that this ratio is approaching, right? And it is definitely less than 1. Then we concluded convergence. And I would like to show how can we conclude that it's actually explanation. All right, first thing you do from there is that let capital R be a number in between this R and 1. Is it possible? If little r is computed like this thing is given. So we calculate it is approaching R, and we want to choose a number in between R and little r and 1. There are many numbers in between, right? Like a midpoint. So whatever you choose, we choose this fixed number in R. And what we know is that this AK plus 1 divided by AK is very, very close to R. That's what it means is approach to R, right? So would that be fair enough to say for all, the all is the important part, large indices K, AK plus 1 divided by absolute value of AK is very close to R, right? So you gather around R, so let me write this space in here. This is number line, here's a 0, and here's 1, and here's R, and here's capital R. Make sense? Little r is less than 1. And this number, the ratio, is all gathered around, just around the corner of this little r, and very further away from the capital R, if it is a midpoint. Make sense? So is that safe to say this ratio will never close to R again? It's down there, close to little r, for all large indices. We don't know what happened at the beginning, but eventually this happens. Correct? Yeah. So also they write it like this. For all k, eventually. There are some indices. From that point on, this guy, the ratio, will never come back to this capital R. It's all down there in little r. Okay? So for all k, and where some fixed indices. For example, n is 1000. So the indices of 1000 and on forever, this quotient is all very close to little r, therefore away from R. So it's definite result. It's not approximate result. So what does that mean? It means AK plus 1 is less than absolute value of AK times R. Okay? If this is equal, then it's going to be like a geometric series, right? Geometric sequence. If this AK plus 1 is equal to AKR, that's next term is multiplied by R, next term is multiplied by just a geometric series. What we have is not equal, but inequality, so that we can still use the trick of this geometric series. All right? So this is true for all k greater than or equal to n. Then from that on, I'm going to write down the meaning of this one for k equals n plus 1, and so on. So this is true. This is in general true. So this is like a recursive relation. If I use this first index for which this is true, then is an plus 1 less than an times capital R. Is that right? Good. Then I'm going to multiply R both sides. Then it allows you to go to the next level. Is that correct? Right? An plus 1 multiplied by R and multiply R here. You can apply this result again. AK times R is greater than next index. So this one in here is going to be like this, an plus 1r, and there is this an and r squared. And what is less than an plus r, an plus 1r? According to this recursive relation. Does this one look just like that in the middle part? AKR is there's AKR, right? So here you apply k equals n plus 1. Then it looks like this recursive relation in the left-hand side. So what's in the left-hand side here? Anybody like to volunteer? If this one is viewed as absolute value of AKR, what's the left-hand side in here? AK plus 1, right? Isn't this one supposed to be AK plus 1 inside? If this one is viewed as AK, absolute value of AK times R, is supposed to be greater than absolute value of AK plus 1. Correct? So what is in here? K is n plus 1. K plus 1 is n plus 2. Make sense? So I conclude that I have a conclusion. This is the recursive relations about k plus 1 and k, but repeating it 2 times, I got an plus 2 is less than an fixed and r squared. That's what I got. Is that right? Any questions so far? And I multiply r again, then I have an plus 2 multiplied by r, and here an multiplied by r. So this is r cubed, right? And you look at this as absolute value of ak plus ak times r again. You look at this as in that form. Then what's smaller than this guy? According to that recursive relation, it's always true. One higher index, right? Without r. So here's the an plus 3. Does that make sense? So putting all together, we have conclusion that an plus 3 is still less than an times r cubed. That's what we have. What do you say? Make sense? If I multiply r again, you go down to the next level and so on. So I would like to claim that if you repeat this, and by doing this one a couple more times yourself, you'll be convinced that there is this an all the time, and there will be some powers of r, and down there it looks like an plus this an, capital N is there, and then plus 1 and plus 2 and plus 3, so I can put a k in there. Looks like that. So I want you to look at this previous 3 examples and figure out the relationship between the index right next to the capital N plus this thing versus the exponent of r. What do you see? Here is the first one, an exponent of r here. And here's the second one, exponent of r. And here's the third one, exponent of r. Right? So here is general one, n plus k, and what is the exponent? Seems like it's k, right? So there's something called mathematical induction. I don't know if you heard about this. It's a technique of proving this type of dot 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 in a better way. Just like rather than using dot dot dot, we use the sigma notation and reindexing and subtracting off and things like that. So mathematical induction is a better way. Here I usually do this, but since we're running out of time, I'm skipping that. I think it's believable, right? The pattern is quite clear that you're not just wildly guessing. This is pretty sure this is happening this way. All right, so we have a general formula. All right, so sum of all that nk plus 1, it looks like this. So we're going to write down eventually something like this. So therefore, start from n, I'm going to call k equals a j. The j is a better, since we use k for something else. J going from 0 to infinity of, I'm sorry, this is supposed to be n going from 1, j going from 1 to infinity. And this result is starting from n, so we're writing down like this in n plus 1. And then we're putting absolute value. So because of our calculation is about absolute value of a something, it's a j, sorry about that, j. We're calculating this. If this converges, is absolutely converges, right? Therefore, it's automatically an without absolute value converges. That's what we saw last time. So n is always there in this result. Only the second part is changing, so I changed it like that. So I could have used k. Always confused. Sorry. The k is there, so k is 1, 2. There's k is there. Okay. So I'm gonna write down. It looks almost like this is an plus 1 absolute value, an plus 2, and so on, going forever, right? That's how it's written like this. So if this converges, this is the tail part converges. Whatever preceding before n doesn't affect the convergence, right? That's only finitely many times. N, capital N is fixed. So let's compare this one. What do we know about an plus k? This is what we know about an plus k. Inequality. Each individual term is less than that, so you can write down something like this. You know, we haven't proved that this converges, and hopefully, but hope this inequality is still meaningful. All positive numbers, and this one is replaced by something larger, right? So it's an times rk, right? Is that correct? I replace the individual term with the larger term, all positive, and of course the sum must be larger. So what's varying here is a k, capital R is fixed, and n is some definite index. Now on we have this nice result of inequality. So these are all independent, constant relative to the index k. So I can pull that out. Is that right? That's a constant. An can go outside. And we have k going from 1 through infinity of rk is what's left. We know how to calculate this guy, right? Correct? Who knows how to calculate this one? Series going 1 through infinity and r to the k. What kind of series is that? Geometric series, right? Geometric series. And what is the first term of this geometric series? K equals 1. So is that r times... Usually you have some complicated numerator, but it's going to infinity, right? What happened to the formula of the geometric series when this one goes to infinity and the ratio is less than 1? That becomes just 1. 1 minus that r raised to k plus 1, that disappears as k goes to infinity, remember? As 1 minus r. And this is so because of what condition on r? This capital R need a condition to, so that this one becomes that. Less than 1, right? So absolute value less than 1. And it's a positive number. So we got that. So whatever this number, we don't know what an is. We only know the existence of that such an, such that, and they're all gathered down there in little r, and this, that. So what we have proved is that not this one is becoming that. What we have proved that this number, we're estimating, especially about the convergence, is less than this number here. So at the beginning of this discussion of the series or sequence, I showed you two theorems. One is a squeeze theorem that usually get down to some number so you can calculate what L is. And the other one was bounded monotone sequence theorem, right? That only tells you that, converges or not. So if I calculate like this, which property did I establish in their bounded monotone sequence theorem? This infinite series is bounded or monotone? It's bounded. This number has r is fixed, an is something that we just chose, right? So it's definitely bounded. It's a bounded. We got that part. What is the other part we have to explain? Monotone? Why is this series monotone? What does that mean? This is supposed to be just a number. As we change this one to a larger and larger number, what happened to the series, right? That's the meaning of the monotone. Why is this monotone? Obviously monotone, right? Absolute value is a positive term. As you add positive, more and positive terms, it's always increasing. Obviously, increasing as a partial sum. Then this term increasing makes sense, right? If you just look at this infinite series, what do you mean increase? This is number. But if you do more and more partial sum of this thing, and it's increasing, since absolute value of stub is always a positive or 0. We keep adding more and more terms, never adding negative number. Increasing and bounded partial sum, convergent. By bounded monotone sequence theorem. Correct? That's why. This is only the side this thing is convergent. How do we conclude it's divergent? Proof of ratio divergence test. We have the same situation, aj, ak plus 1, absolute value converges to number r, and r is greater than 1. Is that right? R is greater than 1. And we want to show this diverges. So it does the same thing. Here's the 0, and here's 1, and here's r. Here's little r. And we choose this number between 1 and r again. Choose number r. Choose 1. So r is greater than 1, and all this, so for all large indices, this absolute value of ak plus 1 divided by absolute value of k is approaching r, is all gathered around here, so therefore it's greater than capital R. Is that right? Does that make sense? They're all down here, gathered around the little r, because it converges to r. If I choose one number, capital R, in between 1 and r, then all these numbers is away from r, capital R. It's all over there. So we have this inequality. And this r is greater than 1, and it pushes, as we do geometric series again, it pushes away from the 0. All right, so we have inequality ak plus 1 is greater than, this time, little ak times r for all the indices k that is greater than some number n. It's fixed. Eventually it happens. So we don't know how to calculate that n, but we do know the existence of one index. And from there on, the next term is greater than ak by this much, at least. That's the conclusion. Now you're doing this same business of multiplying an r and use this recursive relation and over. Its only thing is different is the direction of inequality, is it not? Exactly the same thing with the direction of inequality. So you conclude on following things. an plus k is greater than the very first one we started with, is an times what number? R to the k. This is what we get for all that. So I wanted to conclude that this one and r is greater than 1, such that if you raise something greater than 1 to k and higher power, that becomes infinity, right? That becomes infinity. So this one is pushing this term to infinity. There is a test that I didn't list down today, but it tells you that when is a divergent, right? The very first test we did, this divergence test. If I can show this one is not approaching 0, then I think that's it. But to do that, I must have this property that an is not 0. If it is not 0, then this r to the k is going to be pushing up. Is there any way we can assert in this condition that there is this first term we can choose in this scenario that is non-zero? If it is always a 0, then it's going to be 0, right? If the terms of the sequence is always a 0, then it's going to be 0 as it's convergent. So if there's a 1 at 0 appeared, occasionally appeared, we can choose that because we're talking about this tail. So I think I explained that. There must be an that is non-zero for some large enough n. If this is not n, you go further and see if there's any non-zero term. If there's no more non-zero term to the eternity of the tail, then it converges. It's 0 all the time. And I don't think we have this result of a quotient being r, right? So this one must exist. So an is a non-zero number, and this one is approaching infinity. Therefore, this inequality pushes this an plus 1, an plus k, approaching infinity. But all we care is that this an plus k, the tail term, is not approaching 0. By divergence test, what does divergence test says? If the tail is not approaching 0, you have a definite conclusion. It's divergent. It's a series. AK is divergent. Right? So that's how you conclude that. So if you look at here, whatever the technical part is, what I just did is that I pull out nice inequality from this limit conclusion, limit result, and be able to compare the actual thing with geometric series. That's what happened. The limit condition approaching r being less than 1 or greater than 1, and I'll be able to compare that with geometric series, and from there I can conclude convergence. If r is 1, this growth rate is too small, so you can't really get any conclusion from geometric series.